The first conic section that we're going to be looking in depth on is the parabola. Now, we've already looked at the parabola in terms of its function notation, looking at it as in the vertex form and the standard form, and looking at polynomial functions. We've really studied the parabola quite a bit already. However, we're going to go more in depth now into the geometry of the parabola. A parabola is defined as the collection of all points, P, so all the points in the parabola we're going to call P. They're in a plane, so a parabola is in a plane. It's not like this three-dimensional figure or surface, that are the same distance from a focus and a directrix. The focus is a point, the directrix is a line. Okay, so two very important things there. So the focus, I have an example drawn up here. Focus is the point, the directrix is a line, and all the points that are an equal distance to both the focus and the directrix are going to be on this parabola. Okay, so if you think about that, what does that mean? The distance between, here I have an example point here. The distance between this point and the focus is going to be the exact same as the distance between this point and the directrix. Okay, that's what it means to be on a parabola. So there's a distance here between a point and another point, which I'm going to call d, little d, of PF. That's the distance between P and F, P being a point on the parabola, F being the focus. And that's going to be equal to the distance between a point and a line. Now remember, the distance between any point and a line, or a line and a point not on that line, is perpendicular. We define it as the perpendicular distance here. So this is a perpendicular segment, and this is d P comma D, the distance between the point P and the line D. Okay, now these two distances are equal to each other. They're defined that way on a parabola. Okay, so the distance between P and F is equal to the distance between P and D. That's the definition of a point on a parabola. Okay, and so that's true for every point on the parabola. If I were to take a point on the other side here, you would get the same relationship. The distance between F and that point would be equal to the distance between that point and the directrix. And it doesn't matter where that point is on the parabola. It could be, down here on the left. The distance to the focus is exactly the same as the distance to the directrix. Draw that a little bit nicer. Okay. So all of these pairs of distances are equivalent. What's also interesting is that there's a minimum distance. Okay, there's one point that has the minimum distance, and that is right here, halfway between the focus and the directrix. It has to be halfway in order for the two distances here to be the same. Okay, that particular point is called the vertex of the parabola. We've talked about vertices before. So the vertex is halfway between the focus and directrix. Okay. So those two distances above and below the vertex are the same. The vertex, I'm going to label it with the letter V. Now there is a line that happens to go through the vertex and the focus and is perpendicular to the directrix, and that line is called the axis of symmetry. Okay, so the axis of symmetry runs through those 2 points and is perpendicular to the directrix. Okay, so let me not write it there. I want to save that space. The axis of symmetry contains F and V and is perpendicular to D. So it contains a focus in the vertex and is perpendicular to the directrix. Okay? All right, so that gives you some definitions and some geometrical features of the parabola. Now we're going to look at what this equation really tells us about the parabola.